Welcome everyone. Today's webinar is a really very interesting one on a really quite a hot topic in the field: foundations for offshore wind turbines, by Professor Britta Beenen from the University of Western Australia, and it'll be featuring some recent UWA research activities. So that should be really very interesting. And just before we get started, as usual, I would just like to remind you that this is an ongoing webinar series, runs fortnightly. So today we have Britta, and in 2 weeks we have another interesting speaker, and we have the schedule until the end of November here. So that's how that is. And so I think with that, I am more or less ready to hand over to Britta for the webinar. So I'll stop sharing my screen, and you can then share yours.
Okay. Thanks, Christian. Welcome everybody. I'm a bit overwhelmed by the attendance. I didn't expect quite so many people. So I will talk about offshore foundations for offshore wind turbines, and I'll feature some of our recent research activities. And so that is mainly work that I myself have been involved in, but of course it relies on many other people, and I'll mention them as we go through. I thought we will start with a brief backward look, thinking that only 30 years ago there was a first offshore wind farm, and how small that was in the day, and how far we've come in just one generation with now the turbines, each turbine producing twice as much energy as all of the 11 turbines of the first offshore wind farm combined. So that has seen very substantial change. And I guess also at the time the North Sea was the emerging market where it all started, and now offshore wind is spreading around the world, with many more regions joining in, Asia and US in particular. Most of the offshore wind turbines, of course, are still supported on monopiles, some on suction bucket jackets now. And so I will talk about both of those foundation concepts, and broadly cover some aspects around installation, but also in-service performance. So this is the overview that will guide you through the talk. I'll start with just a brief look at a project that I'm not actually personally involved in, but I thought this would be interesting to include in tonight's webinar. Installation of monopiles, and in particular through a hard layer or where there are boulders present. So that can lead to extrusion buckling, and a PhD student in our group, together with Mark Randolph, Christophe Godin, James Doherty, has been looking at this problem both from an experimental and a numerical side. And you can very well see that both in the experiments in the centrifuge and also in the corresponding FE, they have been able to replicate the phenomenon. So it does happen. And the first paper is out, or is about to be out. I'm not quite sure where ISFOG is at, but the 2020 asterisk ISFOG has the first results of this research. Now this is proceeding in further stages, including more work, and I think will be quite useful to the industry. When it comes to monopile-lateral response, of course, there we also need to understand solid structure interaction in detail before then taking a step back and being able to develop practical methods on the basis of our understanding. So featuring the necessary ingredient without overcomplicating things. And you can employ a range of methodologies to approach the problem. You can do some numerical modeling, and I've purposely taken some of my own results. So I can only have myself to blame when I say that rubbish in can always be rubbish out. So people are generally quite aware that that needs to be paid attention to. Of course, you can increase your confidence in the numerical modeling by validating that against physical data. And I'm not pitting one methodology against the other. I actually think there is room and justification for all of them, because at the end of the day, they are all models in some way, unless you go to a full-scale installation and test that out. So each and every one has benefits and also limitations. So 1G testing is obviously rather economical, and you can, as was done in this research, look at a very large number of load cycles. But of course, the self-weight stresses in the soil are not quite the same, and you would get higher dilation in your sand, and you need to look at that carefully, both at the dilation and the stiffness. Most people, I would think, in the offshore wind area would be familiar with the PISA project, which featured field testing, and I think that is a very valuable addition to the picture. But of course, is a model, again, done onshore and needs to be incorporated in the overall view of things. So putting everything together really holds the solution at the end of the day, and that was done in the PISA project itself, of course, putting together numerical and modeling and field testing. The methodology that didn't fit on the slide anymore, so I had to put it on the next slide, and people would expect me to mention that, of course, is centrifuge modeling. So yes, you are again looking at a small scale model, but you are increasing the soil stress levels so that they are relevant to the field, and you have established scaling laws that you can work with. So your measured loads and displacements are thought to be representative of your prototype. And this allows you to investigate the performance under in-service loading, having gone through an installation process, for example, and can include the role of the pore fluid response if that is of interest too. Important in that, of course, is that the entire history is performed without stoppage of the centrifuge, because otherwise you would lose that sort of inbuilt stress state that features the history. So it is, of course, more expensive than 1G testing, but it is an economical alternative to field testing, for example. But I think all of them actually play a role. I wanted to include this and touch on the question. So you're looking at a small scale model in the centrifuge. Is that actually reliable, and can you trust the results that you obtain there? A couple of years ago, I was involved with a large number of other people in a global benchmarking project that was actually led by NDI, and we have done an industry showcase on that, where we wanted to build a firm background and show the reliability of centrifuge modeling in this context, and also, I guess, encourage sharing and collaborative research in that space. We did this on a shoestring budget, so the centrifuges are all different in the different places. And the overall experimental apparatus was different as well. Everybody had a different pile, a different loading apparatus, a different different sensors to measure the loads and displacements. And so we agreed on what we can model with what was available to all of us, and then compared what we got out of it. So the consensus was we are all using dry sand. We would all model the same prototype, but with different models. We would install the monopile, but at 1G through jacking, and then it would be a monotonic quasi-static lateral pushover. In the plot on the left here, you can see some of the results plotted in terms of the horizontal load over the pile displacement at the solid surface. And you can see that in absolute terms, the results do differ quite a bit. This was modeling a prototype of 2 meters in diameter with 5D embedment and an eccentricity of this lateral load application of 4D at a relative density of 80%. However, when you normalize both axes, and I guess in particular the load axis, because the tests were all done on different models, they all fall into a very narrow range, apart from a couple where there was an explanation for why that happened, because the conditions at the pile head were a bit different. This has been published in last year's 16 ARC conference in Taiwan, so people, if they want to, can come back to there. It's probably the paper with the most authors that I ever put out. There were a few centrifuge centers where we could also model a larger monopile, because you might think 2 meter diameter is not really a monopile. So we could also model a prototype diameter of 5 meters. The rest was all the same. And again, when you look at the normalized load displacement response, that all lines up pretty well. As I said before, this was a jacket installation at 1G, which was simply due to the fact that we could all do that without modification to anything that we had. Common numerical assumptions are to wish the pile in place. You can, if you look at it from a research angle, you can jack the pile in at 1G or at NG in the centrifuge. Normally it's impact driven in the field. Does that actually matter? Well, there is some evidence from installed offshore wind farms that was published by Mats Damgaard in his thesis from 2014, that the eigenfrequency that was measured in the field, and that's the stars here, was different to the calculated and lay between the calculated and the fixed. So there's clearly something that is a factor that wasn't part of the calculations and perhaps isn't fully understood. And one possible reason is that the installation process could play a role in modifying the solid state to then result in different initial stiffness. Why does that matter? Most people would be familiar with a diagram like that, where the frequencies, the forcing frequencies of the wind and the wave spectra are shown here, and also the rotor and blade passing frequencies of the wind turbine itself. And generally, the offshore wind turbines are designed to have their eigenfrequency fall into this narrow band here in the range that's denoted soft stiff. So it is quite a narrow window to start with, and then you want to give a little bit of bit of safety, I guess, in narrowing the window by factoring up your 1p and 3p frequencies. So you don't really have a lot of wriggle room. If you happen to think that your eigenfrequency, say, sits here, and then you're out by 15% this way, then you may actually be in a place where you don't want to be. This wasn't particularly great English, but I hope you could follow my explanations anyway. With that in mind, we designed some monopile experiments, and we performed them in the centrifuge. And essentially, as I said before, our goal really was to be able to perform the entire test in one go, so to speak. So we prepared soil sample, and I should really say that this is work by a PhD student who submitted this year, Sheng Fan. He has tackled this complexity with a lot of spirit and made it all happen. We prepared the soil sample, put it on the centrifuge, spun it up, and only then did the pile penetrate into the soil. So it was suspended above the soil before the stress levels in the soil were where we wanted them to be. And this was possible with the contraption that you see in the photo here. So you can see the pile, which is also shown a little bit bigger here in the photo in the center. Before we penetrated the pile, it was held up through this clamp. And then we have a miniature pile driving hammer that we can use for impact driving of piles in the centrifuge. So we could lower this down in a controlled fashion through the actuator to have the monopile penetrate under its self-weight and then impact drive it in. We use this collar as a pile driving guide, but then also to facilitate the lateral pushover, and you can maybe see that in the bottom picture here. And then we had a pair of laser sensors to measure our pile displacements, so we could deduce what the global response was. The results of two of the tests are plotted over here on the right, again in normalized form, where you see the pushover response of the pile that was jacked in at NG as the black curve, and the impact driven as the red curve. And it's quite clear that the impact driven pile both has a higher initial stiffness, but then also actually keeps that and has a higher capacity throughout. So to give you an idea, a normalized pile displacement of about 0.04 corresponds to about a degree of rotation at the pile head. So this is well beyond serviceability criteria. So this is what we measured in the testing. We then wanted to use that to validate a numerical model and be able to investigate this further. How did we do this? We used the CEL technique in Abacus for the large deformation problem of the pile installation. The pile was modeled as rigid in that phase, and we captured the sand constitutive behavior through a hyperplastic model with the parameters all shown here on the right here. We assumed a general contact of intermediate roughness, and in the first instance modeled the experimental pile. So we did allow for the epoxy coating on the strain gauges, even though the bottom part of the pile had a thinner wall thickness, and that also was reflected in the fact that the inside of the pile was left as a smooth interaction. Sheng looked at jacked and impact-driven installation, and these are some of the results. I do want to go back and point out that hopefully this is going to come out very soon, and I abbreviated the the reference there, not to crowd up the slide too much. On the left here, the two images shown represent the void ratio following jacking on the left and impact driving on the right, where I guess this yellowish color was the initial void ratio before the pile penetration started. And you can see that jacking in this condition resulted in quite a small zone of influence around the pile, a bit of heave here. Impact driving, on the other hand, affected a much larger zone of soil and resulted in quite significant densification, as you can see there. The two images on the right show the horizontal stresses, again following jacked installation on the left and impact driving on the right. And you can also see quite significant differences, both with elevated stresses below the pile and affecting some area around the pile, but quite visible differences. This was for a relative density of 38%, as we had in the centrifuge experiments as well, but we have since looked at other conditions also and another sand too. So where do we go from here? I'm not going to be able to show you everything, given that it's also not fully published yet. The pushover is shown in the companion paper that I've hinted at here. And that was done by mapping the results from the installation model to a small strain model, again in Abacus, to look at the lateral loading. And the mapping was done via MATLAB routine, which included actually tracing the soil surface as it was following the installation process. We have included in the lateral pushover from wished in place conditions, and you can see that even as you go to 1 degree of pile rotation, so 0.04 D roughly, there is very little change in the void ratio from the wished in place conditions. The stresses do change as you would expect them, but that also means that the soil state that we had resulting from the installation in the jacked and impact driven case really do govern the lateral pushover phase as well. So over the area of serviceability and beyond. I would like to say that, as you've seen before, that the pile was, or the pile wall thickness was somewhat enlarged in the experimental pile, and therefore in this numerical validation also by the epoxy that we had on the strain gauges. So the D on T was slightly lower than what you might expect of a full-size normal monopile. And also the diameter itself is a little bit smaller than perhaps your current monopiles now, but we've since looked at that numerically too. The numerical model allows us to extract PY curves, and as you step through the various embedment depths of half-foot diameter, 1.5, and 2.8 diameters down, you can see the differences between the respective PY response of wished in place, jacked, and impact driving, where the impact driving comes out on top in all four depth, but the difference between the different installation methods, of course, changes with the respective soil state. One little plug for a research project that started this year. Vibro-driven piles are gaining a lot of attention, in particular in the offshore wind industry, and we would like to support the industry in advancing the understanding of what is actually happening in terms of geomechanical processes during the vibro pile installation, and again what effect that has on the pile response under lateral loading. So we follow a similar methodology. We will supply a few more soil element tests, but then look at centrifuge testing, again with full model and some PIV tests. And currently we're in the phase where we're developing a model vibro driver for the centrifuge, which turns out to be quite challenging if you want to satisfy all the scaling considerations, but we're getting there. What a great PhD student. And also, of course, try and complement that with numerical modeling, where, of course, there are also challenges because it's not only a very large deformation problem, it's a very thin-walled object penetrating many, many times the wall thickness into the sand. The sand needs to be modeled with a constitutive model that can capture the change in soil state, but also you would want to go towards introducing the fluid phase as well, and there you definitely have to move away from CEL because you cannot introduce proper interaction. Your contacts will always be, your contact interface will always be looking at total stresses. So that will be very much overestimated. So, so much for monopiles. I would like to turn my attention now to suction buckets. And I've shown pictures here of suction bucket jackets that have been installed. The first one was Borkum Riffgrund 1 in 2014, and then of course Borkum Riffgrund 2 followed, and Aberdeen Bay has also been operational now for a little while. But there are some more happening and further in the pipeline, and there have been quite a number of trial installations of suction buckets. Unfortunately, they have remained largely confidential. As with anything, the installation to target depth is critical to ensure the performance of the foundation in service. And so it is important to understand how suction is transferred, or is suction transferred at all, in particular in layered soils, where perhaps a less permeable layer like a clay layer could hinder that, and how is the soil state changed, and does that matter for the in-service performance? So we've had a look inside suction buckets, and this may not be completely accessible to you if you haven't seen it in the flesh in the centrifuge, but in essence this is a bucket cut in half, so you can see inside. We're doing everything else that we do. We have a connection to a pump, we have a valve that so we can direct the fluid flow. We have a connection to an actuator so we can measure the loads and control the movement, etc. But we can also take photos of what is happening. So we had a look at suction bucket installation in sand to, I guess, confirm what is happening and to pave the way for other stratifications. And I've included some results here that have been published. Raffaele Ragni led this research, and this has been contributing to a much larger body of work now in this area. So at two different penetration depths, you can clearly see the mechanism during the suction installation phase in this very dense sand, and you can also notice some areas of piping where there's extension or compression. I should say that in order to make these very challenging experiments feasible, we had to opt for slightly thicker skirts. So the plug heave that you see here, so the extent of the plug over the original soil surface, may look more dramatic than what it actually is. During the suction installation phase, most of the soil moves inside the bucket, and so a lot of this, particularly down here, is due to displaced volume. But then we have an idea of what is happening. What does that mean for the in-service performance? The PIV images and the analysis that were done on them was actually done, what I showed you there was in an installation with a very high pumping flow rate, so basically worst case scenario in terms of loosening of the sand. And what I showed you also was towards the end of the suction installation phase, so before the pumps were switched off, etc. Since then, we have looked at what happens afterwards. And this picture here from Mark Stapelsfeld's work shows you results of CPT tests, where the cone was penetrated either just in the sand in the box or through the lid of the installed bucket. So the cone was in place at the time, and then we could do the CPT test after the bucket was fully installed. You can of course see that in the bucket, in the CPTs through the bucket lid, the cone trip resistance is higher because of the confinement and the fact that you're penetrating an object through the soil plug. But you can also see essentially a group of curves that's more or less bilinear and others following a different trend. And we deduce that the soil state really is dominated by the lid contact and the confinement, of course, inside the skirt once suction installation is complete. So the role of the pumping flow rate, we couldn't detect any significant difference in the test results that we saw here. So we made the conclusion that once the bucket is installed, whether you've installed it faster or slower doesn't actually make a difference to the in-service performance. What does make a significant difference, and the more recent work has confirmed earlier work, so the 2018 work was done in a different sand, but we've added to this and confirmed the general trends, is that the drainage regime that operates is a critical factor in suction bucket performance. So what you see here is results of a single suction bucket having been installed in dense sand and then with a cyclic loading history applied to it with slight average compressive stress and a decreasing number of cycles with an increasing magnitude of load, and the sequence was then looped again and again and again. And you can see in the results plots over here that the effective permeability makes a significant difference to the overall response, where the black line is the applied stress, and the blue lines is the excess pore pressure measured through a pore pressure transducer underneath the bucket lid. And so if you have permeability of about 10 to the minus 4 meters per second in the sand, for this particular condition, we observe that slowly there is some permanent upward movement of the bucket due to the cyclic loading history, whereas if the permeability is slightly lower by a factor of 3, the picture changes quite significantly. So this is actually within the accuracy of being able to measure the drainage response, but it is significantly important to what the bucket does. The results that we obtained included a number of different scenarios, and I'll show you a selection here. The installation history, as I said before, after probing the soil plug with the CPT, was found not to influence the in-service performance very much. Drainage is, however, important. And as we found previously also, the resistance that the bucket offered was well beyond the drain frictional capacity without necessarily any permanent displacement. So the load cycles that we applied went multiple times beyond the drain frictional limit, and that could initially be sustained. And when you went much higher, then you saw the permanent displacement. Mark proposed a simplified prediction method valid for single layer sand in that paper also, and this is shown in the bottom plot here, where you can maybe make out pairs of curves. So against the centrifuge data, we saw very good agreement of the predictions, but of course the proof would be in the pudding if anybody had field data that we can try this out against. Remaining questions include how much does the ordering of the load matter? For a mono bucket that has been explored recently by a visiting student from China, Lumbo Luo, who worked with us for a while and published a paper recently in Geotechnic Letters. But of course, for the suction bucket jacket or the bucket under primarily vertical cyclic loading, you would think that it also matters how the loading is arranged. Where this is all going, of course, is layered soils. So how is suction transferred? Is suction transferred at all? If there is a low permeability layer, probably intuitively the less critical scenario, and that is when a sand layer overlies a clay layer, or you could probably see as a possible concern is that the drainage flow is cut off in the sand, so the beneficial reduction of the tip resistance may get lost towards the clay layer, but that may be less of a problem. The alternative scenario where a clay layer is on top and the sand is below is probably a lot more problematic, because you need the seepage flow in the sand to reduce the tip resistance in order for the bucket to penetrate. So if that's not transferred, that can be a problem. Mechanisms to facilitate that have been postulated before. So this wasn't an idea that we came up with. However, we were able to show that this actually is the case. So initially, as the suction bucket starts penetrating, the suction is not transferred. However, the suction increases, and at a point may be able to uplift or rotate, or both, the clay layer, which then allows at least some suction to be transferred to the underlying sand layer so that the installation can proceed. So we found the suction to be transferable, and the resulting benefit of the reduction of tip resistance in the sand layer to be present. The deformation mechanisms overall were comparable with what I showed you before in the sand-only case, but because of the layering scenario, the loosening in the sand part of the soil plug was actually less. So there was less volumetric expansion. Increasing pumping flow rates pretty much only led to larger final penetration depth, faster installation, and reduced clay plug uplift. So we found that beneficial. So the PIV provided insights to installation. Of course, you want to know about the in-service performance as well. We have done further testing, again with Mark Stapelfeld from Hamburg, and submitted that to the ASC, but it's still under review, so we'll have to watch this space, and maybe next time I can share more. With that, I've pretty much come to the end. I'll give you a brief outlook of some other things that we're working on at the moment, and then I'll be quite happy to take any questions. So we are looking at suction bucket installation prediction, but also further into the in-service performance, in particular in layered soils. And we're also interested in installation strategies such as cyclic pumping, where you don't just switch on the suction, but you may reverse it, as shown over here, which may be beneficial in keeping the required suction down and still achieving your target depth. Another interesting point that we're looking at the moment is lid contact essential, and therefore is grouting required, or could you get away without it? And then how can we better predict the in-service performance? How can we make that practical? And the point that I touched before, does load ordering matter, and how much is that? So with that, I'll wrap up. I've given you some snippets of our recent research, probably showing that it can be quite complex, and while we've made some advances, there are plenty of challenges still left.
Thank you very much for that, Britta. That was very, very interesting. And I forgot to mention at the beginning of the webinar that, of course, you'll take questions. Now, I send a message. So we have quite a lot of questions that have been typed in already. But if anyone is interested in asking a question live, then please raise your hand and I will unmute you to allow you to do that. But while we wait for that possibly to happen, let's take a few of the other questions. You mentioned, this is actually a question of my own, I'll ask that first, if you don't mind. You mentioned that the resistance of the suction bucket is well beyond the frictional resistance.
Intention, yeah.
What well beyond is not a very well-defined number.
I don't really want to give a very specific number either, but we have included also previously that it does go several times beyond the drain frictional limit, and you're pressing me for a number now. I can't remember whether it was.
So it's undrained somehow, right?
Yeah. So the load sharing between skirt and tip and lid, also then in compression, becomes quite complex, and you can see differences between the tests when the effective permeability in the sample is slightly higher or lower. So that definitely shifts how frictional the response is or how undrained it is. And of course, over many cycles, it is drained. So the partial drainage or perhaps even initially undrained response is only very short term. So yeah. It's only. It
would have to depend quite severely on the dilatancy of the sand, wouldn't it? As well, or sort of how much undrained capacity you can rely on.
Yeah, I mean, if you do an undrained pull out of the bucket, you can show exactly what Guy and Byron have summarized in their 2005 paper, that in the shallow water that you're in is kept by cavitation, and that's exactly what happens. So you mobilize the undrained capacity and then you follow the cavitation cutoff.
Great, thanks. let's take a few questions here. So this is in relation to monopiles. What do you think about making the pile tip thicker and heavier, but sharper to avoid pile tip damage? So basically,
I'm not sure that I can field too many questions on the pile tip damage, and I would refer you probably more to my colleagues. It is obviously influenced by the wall thickness, but I think also the overall geometry and a number of other factors. So I'm not gonna be definitive on that one.
Sure. Your Vibro scale driver, will that be the first one of its kind? Is a question.
It would be at the moment, so hopefully nobody beats us to it. Yes.
Okay. Great. Then there's a question on liquefaction. I don't know if that's something you can say a few things about, or if it's something you've studied.
Is this, I'm not quite sure which question is it? Do you want to?
The question is if wave loading can basically induce a liquefaction.
Indirectly is the answer. So in the experiments, we have saturated soil and we have free fluid, but we're not introducing the wave action through actuating the fluid. We have deduced load histories that we think are reasonable to be transferred to an individual suction bucket of a suction bucket jacket, and we've taken the bucket that would face upwind essentially as the critical one, because that'd be most likely loaded vertically and most likely to go into tension. So we do apply the load to the bucket, but not through wave loading. So then the soil structure interaction happens with how we actuate the bucket itself.
Okay. We have some raised hands. I will unmute you, Niklas.
Yes. Can you hear me?
Yes, I can.
Yes, a very nice presentation. Thank you for this excellent presentation. I have a question. You showed a large difference in the horizontal response between a jacked monopile and driven monopile.
Mm-hmm.
The driven monopile, of course, exhibited a very stiffer response. Could you know that if this divergence, if this difference in the horizontal, in the monotonical horizontal response is being sustained during a large number of lateral horizontal wave loads?
We have not modeled large numbers of cycles, neither in the experiment nor numerically. In the experiment, it would actually become less economical, and I would go to 1G testing for that. And actually, Pablo Cuellar's work that I showed earlier is an excellent example of that. Numerically, we have looked into the effect of a few load cycles that you can model cycle by cycle, but I don't personally see the point in modeling large numbers of cycle that way, because it's vastly computationally expensive and will become inaccurate. And I would probably look towards a model where you model only a few cycles, cycle by cycle, and then you extrapolate the trends, such as the high cyclic accumulation model by Thorsten Wichtmann and his group. I think that's much more suitable.
Okay, thank you very much.
And they have recently published something in that vein.
So until now you have focused on the vertical loading, on the cyclic vertical loading, and on the effect of the initial conditions on these loads, on the vertical loads, and on let's say on a few numbers of cyclic loading.
So maybe I've confused the issue. So we have pushed the monopile over through lateral loading, just
Yes.
increasingly pushed it over, or separately in another analysis applied the lateral loading in a cyclic fashion. We didn't do that axially.
Okay.
Yeah, but that's something that we will do in the Vibro-driven pile, because I think people are interested to know both the axial response. Our primary interest would be in the lateral response, but
Yes.
we'll include a little bit of that too, if and when we get to that.
Yes. Okay, thank you.
Thank you.
Thank you, Nicholas. And we have one more. Jorge. You can unmute yourself, then you can talk. I think that's what you need to do. Oh. Okay. He's coming in. Hello?
Hello.
Hi.
Yep, we can hear you.
Hello, everyone. So I have a question. You mentioned something about the grouting of the foundations, and I was eager to know if you could give us some insights on implementing a jet grouting solution for the improvement of this of the foundations. That's it.
If your question is in relation to jet grouting and suction buckets, I'd be quite hesitant. The purpose of the grouting would be to fill any void that there is between the top of the soil plug and the lid invert of the suction bucket, to just make a good connection essentially between the foundation and the soil. So providing that connection, filling the volume, but not inject that with any significant pressure, because you don't really want to do anything to the soil itself. There isn't any need necessarily, unless I've misunderstood your question.
All right. No. Yes. Thank you. That was really good to know. Yes. I'm pleased with the answer. Thank you for the great talk.
Thank you.
Thank you, Jorge. And we'll take one more. Hansini.
Hello.
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 Hello. Thank you very much. It was a very nice presentation. Can I have one question on cyclic installation of suction bucket? Have you published anything regarding the cyclic installation of suction bucket? Because in my project, I have been working on our company has proposed to use cyclic installation, but the information and literature we have is very limited.
That was the impression that we got as well. We know that through the trial installations, there's obviously some data available on those, but that's confidential. But besides that, there isn't really anything very much in the literature. There are two papers in the 2017 SUT conference proceedings, and one of them I showed on the slide. So that I think is pretty much the extent of it. You can draw some more, I guess, knowledge from soil element testing, CNS testing, and axially loaded piles, but of course neither of the two really fully replicate your conditions. So quite significant uncertainties remain. We haven't published anything yet. We had wanted to put something in ISFOG, but then didn't obtain enough conclusive evidence to the submission date, so we had to pass. But that is forthcoming.
Okay, thank you very much.
Okay. Just one interesting question that came in that I'll just ask. It's a more personal question, you could say. It says in your 2018 geotechnique paper on suction buckets, you conclude that tensile load should not be considered in design yet due to lack of knowledge. Do these results here change that recommendation in any way?
There has been a growing body of evidence that suction buckets do perform beyond the drained frictional limit. However, I would still urge caution for a number of reasons. I mean, firstly, you need to be safe in what you do anyway, so you don't want to push the envelope too far. Secondly, the permeability is an uncertain parameter, and that can have significant effect, as you can see in the plots here, but also in our previously published results. So I would be hesitant to push the envelope too far, but I think limiting everything completely to be within the drain frictional limit is probably a bit conservative.
How much faith would you have in numerical analysis to make that assessment of whether you have the conditions are such that you generate enough with sufficient pore pressures? I mean, you say the permeability, that's sort of an uncertain quantity as it is. So. Yeah.
You want to have high confidence in your numerical model, and in particular in the interface interaction. So how you model your interaction at the skirts, but also around the tip. Yeah.
Okay. We will unmute one more, Mr. Kumar.
Yeah. I think just flip back to being mute.
You need to unmute yourself. Okay. There was one on the increase in horizontal stress. I think you've answered that already. The increase in horizontal stress is for the two cases. Let me just see.
That refers to the pile, I assume.
Yeah. Just one question on the on this benchmarking exercise that has been done. Because I thought there was something I didn't quite understand with the comparisons you made. You compare different piles with different dimensions, and then scale them to have to show that you can do that.
Yeah, so maybe I went over that a bit quickly. So the pile dimensions that we had in the different models in the different centrifuge centers, they were different, but we were all modeling the same monopile. So with your scaling that you do, for example, if you test at 100G in the centrifuge, then you would scale your geometric dimensions by a factor of 100. So You could model a 5-meter diameter monopile with a 15-millimeter steel tube in the centrifuge. And so we were all aiming for the same prototype conditions, but we got there in different ways. So some had larger, some had smaller pile models, and they were then tested at higher or lower G levels. But we're all aiming to model the same field conditions.
Okay, and you showed them that worked. That was the
yes.
Yeah.
And there was also a subset of results that was where the testing was done at IFSA in France. They included a few tests and went through a modeling of models exercise, which is exactly that. So you can test the same prototype conditions at a lower G level with a larger model, or at a higher G level with a smaller model, and they showed consistency within that as well.
Yeah. So with the driven piles, the driven piles, you mentioned that it's very important to have a constitutive model if you want to model this properly that accounts for soil state, so basically the change in void ratio, because that changes quite dramatically around the pile. What about what about grain crushing? Is that an issue? Because it's not so much a question. There's also a question of void ratio, but you create a very different new material in a way.
Yes. Yes. Interesting question, and room for another PhD, I think. Yes. So. There are conditions where you obviously get very high stresses, in particular under the tip of the pile, and if you were to consider that, you might want to consider grain crushing too. That wasn't a complexity that we were willing to tackle in the same go.
Sure. So maybe we should just take one more. Yes, I mean, this is a common question. So, are there any good books you can recommend that cover this kind of thing?
I think we're having some feedback in the line now. I think somebody else is unmuted now. Can't really hear you very well.
Uma, can you hear us? Yeah. Okay, I don't really going through.
I can't hear that now. Do you want to repeat the question or direct me to where to find it in the chat?
Yeah, the last question in the chat. Books or literature on this type of subject, offshore wind turbines.
I think half of that got lost. I heard in the end offshore wind farms, but that wasn't particularly.
Okay. Okay. So I'm dropping out. The question is, are there any good books on this type of subject, the offshore wind turbines, that you can recommend?
I see. I'm not sure that I'm completely up to date with books in particular. I certainly do know one or two that have come up, but the body of literature moves so quickly. I would probably be more drawn to journal publications that come out more frequently, because books can date quite quickly on that front. But there are a few books around by reputable people, so I would go with that. Yeah.
Thanks for that, Britta. I'm afraid that's the last question we will have time for today. I know there was quite a few others, and I apologize for the ones we didn't make. I would encourage you to get in touch with Britta directly and continue the discussions. And so with that, I would like to thank you all for attending, and I obviously hope to see you next time in 2 weeks' time. And so yeah, thanks, and see you next time.
Thank you very much.